Hi, welcome to the third and the last video on the topic of trust region policy optimization. In this video, we will discuss the implementation of this reinforcement learning algorithm in Python using PyTorch. So as a disclaimer, I've used two different implementations. One is pretty popular by user I. Kostrikov on GitHub, and another on implementation by OpenAI. Both of these implementations have their problems. For example, OpenAI's case is not easily readable, but say the Kostrikov's implementation is, but his implementation is kind of short, lacks features like cases where you have discrete action space versus continuous action space. In this case, only continuous actions can be implemented, while OpenAI, they have a selection which approach to use and whether to use natural policy gradient or trust region policy optimization. So yeah, let's briefly recap what we've done previously. If you haven't watched the previous video, I guess it's not that important, but we will cover main ideas right now, and if you're interested, you can watch it, or there are different resources in the description which I recommend. So if you remember trust region policy optimization, it kind of has the same performance metric for our policy, which is just expected discounted rewards, but they introduce new kind of equation, which is kind of policy improvement, and we've discussed basically how to transform it, because you see there's an expectation over data which is basically gathered using new policy p prime, but then other internal stuff, all the advantages or rewards, they are gathered, they are evaluated at old policy. So we've discussed how to turn this expression into something that only uses old data. And so yes, we've introduced the importance sampling to change the expectation over old data, but then we've concluded that actually in order for this expression to fully hold, we have to force the what was called visitation frequency for both policies to be similar. And so it's kind of, in my interpretation, it's the step where KL divergence comes in, because for two different policies, for them to have similar visitation, basically frequency, that means they have to do similar actions, choose. That means that their policy at each state have to be somewhat similar, right? And basically, we know that we kind of can define some kind of metric using this policy improvement, and then we want to basically improve this metric using something like gradient ascent. That means that we have to take a gradient, find the gradient of this expression. The objective function here, so people refer to it as a surrogate reward, is this, which includes this importance sampling. You can take gradient analytically, because we're searching for a gradient with respect to policy's new parameters. It just diffuses inside of this expression due to linearity of expectation and summation. We will return to this a bit later, and we repeat pretty much the same procedure as we did in the natural policy gradient when we have defined an optimization problem by by basically using first order approximation for objective function and second order approximation for KL divergence. If you remember that we wanted to maximize the objective function, but under the constraint of this KL divergence, which said that our new updated policy cannot be much different in not in geometric sense, but not in parameter difference geometric, but in kind of parameter space distances. And so we can achieve something like pretty much the same as natural policy gradient update. This is kind of the, where do we have it? Basically, it's step in parameter space, how far, in which direction. I mean, you should go KL divergence, okay. But again, about the natural policy gradient, it kind of used the approach of this second order approximation of KL divergence. Where was it? Right here. And we have derived that we can express it via Fisher information matrix. Here we kind of we won't do exactly this. We will try to calculate KL divergence and then take the mixed derivative, second derivatives. But in natural policy gradient, what we had is we had this term in summation gradient of log of probability, and we could have built gradient of this NPG performance using this term, and also the Fisher information matrix could be constructed as an outer product, expectation over outer product of these terms, right? So we actually won't calculate the Fisher information matrix. We will take the derivatives, second derivatives. So yeah, that was the final expression for policy parameter update, where we have introduced the direction in which to update and the step length. And this epsilon was determined by KL divergence, because this epsilon dropped out during derivation, and we introduced it here in a step length. But still, you have to understand that this Hessian is just an approximation. It's a quadratic approximation of whatever it really is. So in a sense, the idea of TRPO is that maybe natural policy gradient actually can violate this expression. And if you remember, in reinforcement learning, if you make your policy really bad, not really, but marginally worse, you can start producing bad data, and you start training on this bad data, and so kind of the learning process breaks, right? Why we want to actually calculate this second order derivatives of KL divergence in TRPO is because we can use, we see this term H inverse times G. In total, it's kind of optimization direction, and we can use conjugate gradient to actually compute it, just this inversion. But in fact, due to properties of Hessian, because it is a second derivative, and you can kind of decompose it into Jacobian of a gradient. And in this optimization procedure, we see that in kind of this matrix A is our Hessian. So there are only steps where this Hessian appears is when it multiplies some kind of vector. But there's called Hessian vector product. In paper, it's referred to a Fisher vector product, because pretty much they are the same, at least under the second order approximation. So we can kind of use this trick when we pre-compute gradient of KL divergence. Then we create kind of function when we multiply this gradient by some kind of vector, whether it is this x or d, whatever it is, arbitrary, and then it turns into a scalar, and then we just take gradient of the scalar. It allows us not to compute full hashing, but in fact we do both computation of hashing and its inversion using conjugate gradient without actually constructing anything, only doing gradients. So that's cool. So our policy update turns from this expression into this expression. And in the algorithm, it's written like this. This x star is a result of conjugate gradient. Usually it's only approximated using very few iterations. I said we will kind of do this, and this is not correct because we don't know h. We don't compute h, but in fact it is just this h x star is just a last iteration of our conjugate gradient, so I kind of lied. Okay, so about policy, it's very boring, but we are parameterizing it depending on whether states are continuous or discrete. And I will just show you the code, and I will basically touch on it briefly. So yeah, let's see. I didn't know how to actually tell you about this part of implementation because I don't think it's useful to. It will be just a waste of time if I will just describe every line or program it from the beginning. So I assume that you're already familiar with reinforcement learning, how to set up a loop for gathering data and such. Although I will show you my kind of take on this, but I will not go in detail. So here's a little graph of how basically we are gathering state action trajectories. And we remember that our objective function includes probabilities of taking action from some state, probabilities of gather which we acquire from new policy and the old policy using states and actions taken in the with the old policy. So in a sense, we kind of, when we start up this algorithm, there is no new policy, right? We can only gather the old policy. But I will tell you now the procedure, it will be wrong because we can simplify it. But we will see few steps which are included in either implementations. So maybe you won't be confused why they do that or any other, and why say in this implementation they are not using the surrogate reward. At least it's not described there, but they're actually using it. So okay, the idea is that, of course, we initialize the agent, we reset the environment, it starts at some state at time 0, and then we send this state into our neural network that will return us some kind of distribution from which we can sample the actions. And we take this action and just follows like usual. This action brings you to the next state, it gives you some reward. But what we kind of have to do, first of all, we will be using importance sampling. That means we can actually, each time we sample an action, each time we have access to this distribution, which is generated by a neural network, we can actually remember what was the probability to take this action. And for KL divergence, we actually want to remember the distributions themselves, either fully, like in discrete action case, or parameterization, like in continuous case. So in a way, what you can do is to gather them as you go. That's what I did previously, but there are reasons why I decided not to do it later. What you must understand that during all this procedure of doing this inference, generating these distributions for actions, right? Our neural network, it stays constant and deterministic. We can just remember which states we travel through, and then we can generate all the probabilities after, because neural network didn't change. So yeah, the difference is that which kind of information we will gather, it will depend on whether our actions are discrete or continuous. In a discrete case, we will use categorical distribution, which is nothing else than a list of length same as number of possible actions, and each entry will just have the probability of taking this action, right? So they sum up to 1, and extracting action 2 is just simply taking first index. So or continuous, as we discussed it previously, we will parameterize it using Gaussian distribution, multivariate, normal Gaussian distribution. So it will have a it will have a covariance matrix which will be diagonal and without covariance of diagonal basically elements. So they're kind of independent. So okay, we've gathered this kind of trajectory using old policy. And then we ask a question like, what is the new policy? And maybe not obvious choice, what to do is to select the same policy and treat it as a new policy. And so what you do is just what's important here to remember when we will take when we will search for a gradient of this objective function, we will have to differentiate with respect to new policy parameters. So in fact, we will have to enable gradient calculation. We will have to enable the computational graph, so it captures the relations of how each action is achieved, right? And so then we will differentiate this objective function using all this computational graph. So kind of this naive approach is that we gathered old policy, old probabilities and such, old trajectories, and we just repeat this calculation of probabilities and such using kind of same policy, but just with a gradient enabled. But what we can observe, actually, if we write it out, say our L is objective function, and then we differentiate with respect to new parameters, it goes inside, as we've seen in the notes, kind of the expectation over old data, but in reality, if on the first iteration we just make them equal, there's no difference between two policies and the rewards which they yield. So basically we can see that if we equate this new and old policy, we will just get this ratio, which we can remember as you can write it as a gradient of a log of probabilities of a new policy at each time step. And that's nothing else than the natural policy gradient update. So in a sense, I would say maybe here they estimated exactly this. What you must understand is that we calculate the optimization direction only once. The backtracking this line search will follow, but it will not deviate from this direction. So gradient is calculated only once. where were we? Okay. So what did I do? Okay, first of all, maybe it's not written here, but if you calculate the KL divergence, you will have to do this trick. Okay, what you could do, like, is to calculate the probabilities and such with gradient enabled. So you kind of calculate the new policy, and then you kind of copy it and disable the gradient and calculate your gradient of a objective function. And that's something probably you can see in the Kostikov solution, where he basically I don't remember right now, but yeah, but basically he calculates something, he enables the gradient for one, and he disables the gradient for it as a second version. So it's kind of we will do this with the KL divergence. But in a case of just calculation of gradient, we can conclude that we actually can do the natural policy gradient update at first iteration. So okay, again, as mentioned, you can calculate, you can kind of remember and keep the batch of memory as you roll, as you unroll. But what I realized, there are environments where basically with a delayed reward, there are actually many such environments, such as mountain car and such, when you get only negative rewards, and in the end you get positive at the termination. And this approach of policy gradient, it's very weak with respect to this kind of task. It kind of means that you have to reach the end of the episode in order to properly understand where the real rewards are, basically which actions you should take. If you only train on basically penalties, it will not work. There are algorithms like probably Q, something with action state kind of learning, which can solve. So they kind of decrease the value of some action in some state, but not in this case. So in this case, and you can see it in literature, that we have to actually brute force, like Monte Carlo approach, when we say, okay, just when you start learning, you just trash around and try to randomly reach the termination point, and then you can start to learn something. So it's very weak. The beginnings are very, very, very slow. So, and what I do, I say, okay, gather me using this policy like n successful trials, and that means it tries to gather one. It didn't reach the termination state in some amount of steps. I say kind of restart, and then it reaches, and then it starts basically calculating next whether it reaches or not, and I will show you. But what I realized, that if you track the gradient along all these tries, there are so many tries that are discarded, so it's kind of waste of computation, in my opinion. So it's better to just compute this stuff without gradient, just by sampling, just by inference, and then kind of run through determine all the probabilities on kind of solved trajectories. So yeah, maybe let's see what we will discuss. So yeah, there are continuous here examples of environments which I've used. Some of them kind of work, and some of them kind of work very, very well and easy. But because of these delayed rewards, some of them are very difficult. Some of them don't even terminate. Something like Lunar Lander, it just begins to hover and basically it doesn't want to terminate. It thinks it's better to keep playing. Discrete environments, card poll is the easiest because every time step is kind of either good or bad in a sense, or in a short memory sense. Acrobot, it's something that I didn't learn it. I guess it was the last one which I've played. Now it's a mountain car. So Acrobot is kind of inverted double pendulum which tries to swing its end higher than some point. It's also kind of, if the policy is bad, you actually may have a very long episode. So it terminates only when it reaches, and if it doesn't reach, it kind of it just takes a long time. But it is interesting for me actually to solve these harder tasks than the regular ones. So okay, this is my chaining loop. We will just look at it just to make an overview. I just initialize some memory because of this problem that if we want to gather only successful batches and we are discarding many tries, I decided, okay, you can just, the easiest is to have a list of states and then you append it, and then this list grows and then it's cut off, it shrinks, it grows. So I decided, okay, I'll make a reservation of space on my CPU, RAM, and then it will gather this stuff, and then it will send to the GPU the successful trajectories. Then it plays these successful trajectories. Here I use the general, some kind of advantage estimator or something, I don't remember. It's very popular. It's a very popular approach. If you're familiar, it's something like eligibility traces. Another is rewards to go, which is just cumulative reward from starting from some time t up to end of episode. Using this rewards to go, I'm training the value function because this is the actor critic kind of algorithm after all. Then I analyze these successful trajectories, I generate all the probabilities and stuff. And here is the idea that your old policy is your new, which calculated with gradients, and you just chop off these gradients. Natural policy gradient, these terms which we discussed, the gradient of log p's, and using this I calculate the optimization direction, but without an inverse hashing. And then what I've implemented during my kind of debugging, that you can calculate this procedure using natural policy gradient approach, where you've used the Fisher's information matrix, and then there's a choice what you want to do. You can, like here, calculate the inverse just directly using linear algebra package, and then multiply to get this optimization direction, or you can just approximate this inversion using gradient descent. So in this case, when we've developed this function which multiplies, which uses this trick of Hessian vector product, in this case it kind of we replace it with the most basic approach, the original, when we actually multiply it, where we generate this Fisher information matrix. So if we are not using FIM approach, we will use the Hessian matrix. As I've said, that means we have to calculate the gradient of KL divergence. Of course, we have to calculate the KL divergence, and we will discuss how to do it. And then we define this Fisher vector product function. When we calculate the gradient of the KL divergence, then we multiply it inside with this argument and calculate another gradient. And there's some damping, which I'm not sure what it does. I mean, I understand that it improves the convergence, but I did not study it in detail. That's what people use in these cases. And yeah, so using conjugate gradient, and we pass this function, we calculate the update direction. And what we do next, we calculate the objective function, kind of surrogate reward. But remember, we don't have to use the importance sampling and such fully, because the policy is the same on first iteration. So we just calculate the NPG, basically objective function, which reduces to just summing up the advantages. We take a snapshot, we detach the gradient, because during not the back propagation, backwards this search, backtracking line search, we will actually use this. So alpha is the step direction. This is default definition of step direction using natural policy gradient. And what I do, what I see the most kind of easy to understand, is that I actually move my policy in parameter space actually at NPG solution. So this is my policy, which has some kind of parameters, and then I say, okay, your weights, just move them by some delta theta. So right, at this point our policy is natural policy, basically gradient result. And what we want to, basically at this point, natural policy gradient stops. And TRPO asks, okay, but is this solution, does it satisfy the KL divergence? And actually what we do is we are using this surrogate reward with importance sampling, because we actually change the policy. Our policy is kind of policy new. It's policy NPG. And we want to check two things. Maybe this step is too long in parameter space, and it violates actual KL divergence. So we want to recalculate the KL divergence. That means we have to compare distributions for each state. That means we have to recompute the distributions using new policy, this NPG step policy. And that's what we do. I just recalculate everything. Also, our surrogate reward actually now is the correct one, because we have to use importance sampling. And these two conditions here are that our policy performance, it either remains the same with this step of length 1, basically, with step length 1 times alpha. So we either want to keep it the same, or actually move back to our solution in direction of -x, and whether it stays the same or improves. Basically, we want to check if improvement remains or even becomes better. So in KL divergence, we just say our step length remember this epsilon in our equation. In this case, it's delta. Implementations use delta. So we just actually want to compare whether it's less or higher or lower than our actual threshold that we are using. And then this my particular approach that I actually moved to this new solution in parameter space. Then what I want to do is I want to start backtracking to the end using smaller and smaller steps. So in one way you can, let me write it. Oh, I had an image, right? When I derive this stuff, it's not kind of important. But yeah, what I wanted to say is that we have some kind of initial theta 0, and then we have direction when this alpha is kind of 1. Actually, it's not this d, it includes the step size, and this alpha should be kind of scalar. So instead of saying, okay, try different set of parameters theta naught plus d, theta naught plus alpha d, and so on, so we shrink it backwards, but every time we use theta naught, in my case I just go to theta naught plus d, and then I just incrementally move backwards to theta naught. You can derive this update rule, so I kind of don't even have to keep the original theta naught parameters. I know the direction is just inverse to our step direction, and you just can say that you iterate through, for each iteration backwards, you just use this step size, which is decreasing. An interesting fact, you can see that this coefficient, using the geometric series, you can say that after taking infinite steps, it reaches 1. So basically it means that when it reaches 1, you've actually backtracked to the beginning, to the minus d. Basically, from plus d, you backtracked backwards. And that's my approach. So I kind of don't have to hold all the parameters in the memory. I just use the direction. Yeah. And so if two conditions are satisfied, just for kind of tracking, I say, okay, this one minus distance traveled, that means how far from the beginning I've traveled. It kind of, we are working backwards, but this is 1 minus whatever we've done, is just how much we moved forwards, right? And there's a case if I have some kind of maximum number of iterations, and then it fails to do this in this number of iterations. What we have to do is we have to return to our initial point. But then remember, I don't store the initial parameters, but you kind of using this definition of how much you have traveled or how much is left. You just say, okay, I just travel backwards, just the beginning in a sense. How much is basically left? I traveled this distance. So yeah, but if it's not satisfied and it's not failed basically by number of iterations, you just keep backtracking just by this step length. Yeah, and there's just some statistics basically to see the standard deviations of my results and such, to make sure it doesn't fluctuate. So this is the overview, and maybe let's take a look at the implementation. So let's start with how the trajectories are gathered. So I make a reservation for memory in RAM, which is the most pessimistic case. Some clearing, it's not really important because I will overwrite on top of it. then, as I said, it may finish one episode, but I ask, okay, using this basically trajectory gathering, get me like 5 successful episodes. So it kind of concatenates them all together. But if some episode fails, it has to remove all the added basically steps which actually led to the failure. And well, what I do just to conserve kind of a code space for the main loop, I just say, okay, every time that we've using reset or steps, that means we know the observations and such, and I can store them right from that point. So we get into the state, and I just store them. We use some action, and I store it. And this batch trajectory gathering is just iteration of my condition, how many I want. And then there's internal, this one is old one, it's bad. And I just keep trying until I get successful trajectory in so many steps. So in this case, I just gather the trajectory, so I don't gather any probabilities and such. I do it actually for advantages. In reverse to go, I also don't need it. For training, what I do here is my policy class. Okay, what I decided to do is define some kind of proto policy. So to begin with, our agent's brain will be neural network, which is sequential. So it's a dense neural network with some number of hidden layers. Input is just number of states. Output is depending on your action space. It may be logits for categorical distribution or so in this case, if we are using the multivariate normal distributions, we want to actually add additional parameter. So in this case, we pass in the state into a neural network, and it returns us the parameters for our normal distribution. So in this case, it will return the mean value vector, and the standard deviation here, it's a log standard deviation for convenience. So I kind of define the subclass in which this second type of parameter is defined. So our proto policy is just outlines the general what the policy should do, and actually there are many basically the same actions, except that continuous and discrete cases will have different implementations. For some, for example, to get distribution, it's a different approach for both. But say for sampling action, it's nothing else, just to basically sample this get this distribution and then sample them. And also for KL divergence, for example, we will store different things depending on which kind of action space we're using. And also like KL divergence will be different for both cases. I don't know if we've spoken about it previously, but yeah, when we want to calculate something like a gradient of a surrogate reward with respect to network weights, if we do it like here, just by asking with respect, because our neural network, the dot method parameters, it returns a generator which contains basically matrices and such, all gathered in one kind of list generator. And when we take gradient, it returns also something which is not kind of continuous flat vector. And so in fact, we have to flatten it out and there's an utility function which does it, but you basically can flatten and concatenate them yourself. So gradients of log probabilities, I actually know that it will have a dimension of how many steps in trajectories I have times the number of parameters, because we take the gradient with respect to parameters. And then I just basically stack them. I create this matrix. Well, one can argue whether it's memory efficient. Where is it? Because in this expectation of gradient, we kind of still store the big matrix, right? But we can do it basically in place. Just calculate one and sum on top of yourself and such. So kind of memory stuff can be mitigated if it's a problem. So gradient, as just we've pointed out, it's the gradient times advantages, and we take a mean. That's our surrogate reward. So this is the ratio. Just using the log rules, you can write the ratio of probabilities times advantages. A Fisher information matrix we've discussed. In this case, the outer product can be calculated by what was it called? Basically not batching, but how could I forget? Broadcasting, it's called, right? And then we take the mean over all the states. We add some diagonal. We boost the diagonal so we can invert it easier. Here's an example of manual hashing calculation. So this is the case when we actually compute the full hashing. We don't use the conjugate gradient, this and the trick. So in this case, we're just calculating the gradient of KL divergence. And again, we know the dimensions, it's n by n, where n is the number of parameters. And we just calculate the gradient of each entry of a gradient in a sense. Maybe we should talk briefly about how to basically manage whether you want to. There are two parameters basically: retain graph and create graph. So the retain graph is basically mandatory for most of our stuff. I'm not very proficient at it, knowledgeable. But basically, each time you use a backwards method on your network, it clears the graph. You cannot calculate any derivatives anymore. In case of the Autograd.grad, which we use for gradient calculation, it's the same. Somehow it's kind of made so it's kind of a final action after which probably network doesn't expect to calculate any more derivatives. So we use the retain graph always by default on true. Now whether to keep the create graph, it just simply means that when you calculate some kind of value, in case this g calculates some gradient of some kind of function which has already gradient attached. So whether this g will have a gradient itself. So if you want to calculate the derivatives of g, you have to force the create gradient. So in our case of hashing, because we calculate the first gradient and we actually want to take the gradient of its elements, we pass the create graph true. But after we've computed the hashing, like I'm not sure if it works correctly, but yeah, after we computed the hashing using all these gradients and such, we won't actually use the computational graph anymore, so I just cancel it, I disable it, and we also add the regularization, basically diagonal boosting stuff. This is the common methods for both approaches, but some of them are not defined. And so let's look at what are the differences for discrete and continuous action spaces. So for discrete actions, we can return to the top. So actually, sampling probabilities, it is the same for both approaches. You just have some distribution, either categorical or normal, and then you just use the sample method. This is the sample action, basically the same. The sampling probabilities, well, there are, where can we take a look at it? In the original, yeah, there is a method. Simply you just ask, okay, what method log prob, and using this distribution, it returns you the log probability of this particular action. So kind of distribution is it's a separate class. It's independent of whether it's continuous or categorical. So it is common for both methods. Where were we? I already forgot. But yeah, but for KL divergence, it's kind of different, because we have to calculate KL divergence between two distributions, and it will be different as shown here, depending on the approach. So in discrete case, again, we are passing the observation into our neural network, and then feed it generates the logits, which then generate the categorical distribution. And then action, the difference between two approaches is what is categorical action when it's sample, what does it return? Because categorical, it returns the tensor of size 0, so it's kind of a scalar. In continuous case, it will be a numpy array. It will be tensor, but we will have to transform it into numpy. So in discrete case, we just take the value. So this batch calculation of all the stuff, which is get the distributions for all the state, but again, we have to extract something else. So in discrete case, there's just a method of probabilities. So you just extract the numbers here, probability of action 1, probability of action 2, and so on. Here we just detach stuff. So we have to detach gradient from everything that we will use, basically, where this prefix all this. So we're just cloning it and detaching it. A KL divergence is very simple. The definition was just actually I've asked ChatGPT how to calculate for categorical case, and that's what we get, which is just these different probabilities, this sum of log ratios and such, and that's exactly what it is here. So we sum over actions, but we mean over the states. So the continuous case, again, it's a diagonal multivariate Gaussian distribution. In this case, for KL divergence, we will gather mean values, which is generated for each state. And then for different versions of policies, we will have different standard deviations. Yeah, we have derived the log probability, log likelihood, I don't know how to call it, but you don't actually need it, because this method log prob, which I've used previously, it much does the same. At least I think so. I've tried it with one dimension, but anyway, I'm pretty sure it will be used. It will be using the same, and it will sum over actions and such. The get policy here, again, neural network generates mean values for each state, and then we retrieve the log probabilities. We exponentiate it because this multivariate normal class, it expects actually standard deviations, not log standard deviations. So in this case, get action, as you see, it returns tensor. We have to transform it to numpy and throw it on CPU, because our gym environment lives on CPU. This batch calculation of probabilities and such, pretty much we retrieve the distributions, and then mean values can be extracted by this mean method. Detaching gradients, KL divergence, we've derived it previously. It's somewhere here in the end, right here. Sum of 1/2, something, something, something. And this is 1/2, something, something, sum. And then we take a mean over states. And here we plug in the parameters of our Gaussian distributions. Okay. I think we've covered pretty much everything. I don't even know what to cover anymore. I'll pause it and think about a bit. Yeah, I kind of don't even know what to tell you. We've covered most of this stuff. Memory, initiate memory, gathered trajectories, successful trajectories, general advantages, rewards to go. We train the value function, which in my opinion is the weakest point in this implementation, because I don't know how to do it correctly. Prepare the probabilities, copied and detached old policy, calculated gradient of log probabilities, so we can calculate the gradient of objective function. And kind of, we already know the solution using the log gradients of log probabilities. Two different approaches. I kind of now rock the Hessian and conjugate gradient. It performs well. We remember the current performance. We move in the parameter space to NPG solution. And then we recalculate all the probabilities in such for this new policy. We calculate the performance of this new policy using importance sampling. And then we say okay, if performance is better than it previously was or equal, and the KL divergence is cool, then we accept this. Actually, we don't do anything because we already moved the parameters in that basically direction. We already applied this solution. Otherwise, we just step back, and if it completely fails to do so, which I didn't see, it just backtracks back and resamples basically trajectories. But usually what you can see here, I'm plotting the second axis from 1 to 5, just so it doesn't overlap with the plots. But it very rarely, actually, there are some cases when backtracking is performed. Otherwise, it just accepts the natural policy gradient step, which is interesting. But they mention it in literature, and in fact, I've also saw on some problems that it really fluctuates. That means that it actually uses the backtracking. The problem again with delayed rewards, this mountain car stuff, it's just crazy, because you have to actually, like I'm doing for one try, I give him 15,000 steps for episode, whether he can or cannot complete it. And yes, sometimes it takes many thousands in order to complete, and in order to reach actually the final point. So in this case, it only did 30 epochs, where it measures 3 successful episodes. But of course, once he measures the episode, it learns something, and then it kind of starts progressing, because at first it just explores randomly. So in this case, it took him like 7 minutes, which is not a lot, in fact, because he's just stumbling randomly. But maybe because I've implemented all the stuff that I reserve the memory and such, and I don't calculate the gradients while he samples, maybe it kind of allows him to work fast. So you see 153 steps to complete the mountain car. In this case, mountain car is what? It continues. Oh yeah. Oh, it's for some, I don't know why, but I think it struggles on discrete mountain car, which is curious. But comparing to classic, basically reinforcement learning approaches, they solve mountain car, I think, much easier. So here I'm training the acrobot, this double pendulum inverted, which has to push its side on top. Actually, like I'm probably not doing this correctly, but my optimization, I just do Adam optimization, and I do many steps. So I actually don't know whether Adam optimizer does it have internal steps, but I've tried to do it with very few steps, and I've noticed just the degradation of performance, basically how this curve evolves. It just kind of starts off very flat, or oscillates like crazy. So what do we get? And yeah, basically, if you see this freezes, it's mostly because my 1,000 iterations. That's what time it takes. So usually, of course, this acrobot, it can basically find the solution pretty fast. So it finds the solution probably faster than my optimization for value function is conducted. But yeah, let's stop him. That probably... Oh no, my kernel crashed. Not cool, man. So it kind of fluctuates, but it grows. Maybe I can measure more episodes per epoch to show actual how the results fluctuate. But it will grow. Basically, I just don't want to wait for it right now. Just to show you that it can work with the discrete cases and continuous. So I guess that's pretty much it. Like, let's just take a last look at this. How to call it? Algorithm description. In this case, they are gathering trajectories, k different trajectories and such, computer rewards and advantages as I have, and value function, gradient as NPG. Here you can see that they are basically summing over trajectories and then taking average over different trajectories. I think none of the implementations actually do this. I'm not sure whether they are gathering, whether they are batching trajectories or not. Probably they are not. Maybe it will impact somehow. So this we are probably already sick of this, we've talked about this. So backtracking, right? Here's this coefficient AJ, and I just go backwards in space, and they feed the value after. So I kind of do it before, but I don't know if there's a difference. So yeah, maybe just, what do we have? Wait. So the value function is just my defined MPL, basically sequential, and the training is just typical, some kind of, again, I forgot. Okay, this learning loop, conjugate gradient, we've seen it. We are missing something, are we? Let's see. I think I wanted to say something, but I don't see it. Yeah. Oh, general, this advantage estimator. Okay, you just can either copy or find it. I just asked ChatGPT and it basically gave the same result as in different literature. Case for rewards to go. I've implemented also discounting, because again I was exploring this problems of delayed rewards, and I think I still use the discounting, which is 0.99, I think 0.99, a lambda, which is for this general advantage estimator is 0.95. Yeah, I also had some kind of variance, this trajectory measurements, for trajectory measurements, when I used truncation, and some cases don't work actually if the, like, imagine the carpool environment, it doesn't have a termination. If it's very good, it will stay balancing together. So there is a truncation point at which you kind of have to reset. But if I don't use a reset, but then there are stuff like mountain cars, which probably have termination point, but it's pointless to terminate until you reach the goal. These are my final comments. I hope we can check the descriptions of different components here. Oh yeah, I have to mention, if you're working on Windows, probably you won't be able to launch Box 2D environments, and I had to install this library in order for them to work. I've also installed C++, some kind of development stuff. I'm not sure if it had some kind of impact, but yeah, I wish you success with your research, and maybe if there will be some kind of problem which is not discussed, I will make another video. Thank you for listening, and goodbye.